Okay, good evening. This is Professor David J. De Los Reyes. Okay, it's August 21, 2023. The time is 10:39 p.m. Okay. My topic for tonight will be Nodal's Theorem. Nodal's Theorem. This is alternating current circuit theorem, and this will now be lesson number 27. So the topic for tonight will be Nodal's theorem under alternating current circuit, and that will be lesson number 27. Okay, let's proceed. The subject matter for tonight will be a long video format discussion. Okay, alternating current circuit, and this will now be lesson number 27. Okay, the title of the topic will be Nodal's theorem. Okay, Nodal's theorem is actually one of the advanced circuit solutions are under alternating current circuits. That is in the computation of a load current connected to a given parallel circuit. The expertise or this Nodal theorem is mostly concentrated on the solution of parallel circuit connections. Like in the superposition theorem, that superposition is best used under parallel circuit connection. And another advanced solution is actually Nodal's theorem. The main concentration is actually parallel connection, okay, of multi-sources. So for Nodal's theorem, the application will be for multi-sources and a perfect parallel circuit. If the given connection of the different sources of EMF are connected in parallel, okay, the best solution for computing the current through a load CL, meaning the total load current delivered by all the voltage sources to a given load, will be by using Nodal's theorem. Nodal's, I think it came from the word node. Node. And the other definition of a node is actually a junction. Junction. Okay. That's why the title is Nodal's theorem, and this Nodal's emanates from the word node, and the other definition of node is actually junction. Okay, to best illustrate the concept of a Nodal's theorem and the computation of, always the computation of the load current is the main problem. Okay? The current consumed by a load CL, if it is connected in parallel with two voltage sources. For the meantime, we are considering two voltage sources. Okay? Then later on, we will adjust the concept for any number of voltage sources. But for the meantime, just to simplify the illustration of the concept of the Nodal theorem, we will just consider for the meantime two voltage sources. Okay, let's try to go with the illustration concept. I will try to give you a figure. So this should be the figure, okay? The connection of this is parallel. Okay? Meaning voltage source number 1, this is voltage source number 2. Z1 is actually the internal impedance of voltage source of alternator number 1. And C2 is the internal impedance of alternator number 2. Because the internal impedances are taken into consideration when we are computing for the total current delivered to the load CL. So this C1 and C2 are not simply impedances. It is the internal impedance of the alternators. Okay, we must take into consideration for the computation to be accurate. And this load CL here is the load. This is the load. Okay. Meaning load, it could be the single equivalent load of a house, a business entity maybe, or a big corporation. So this load CL is a very variable thing. It could be a load from a single house, a load of a business entity or a load of a big corporation. But in general, we term it Z sub L, meaning impedance of load. This is load. So the concentration of the problem under Nodal's theorem is the computation of the current, okay, drawn by this load CL when it is connected in parallel with E2 and E1. That's why I told you a while ago, Nodal's theorem is specially used for multi-sources and perfect parallel circuit connection. Okay, they are in perfect parallel connection. They are in parallel. Okay, let's try to bring out the unknown. Find I sub L using Nodal's theorem. Okay, so before I will try to bring out the general equation and how to compute for I sub L, okay, we'll go first with this derivation. We'll try to bring out the free body diagram. For the first figure, if we try to cut here, right, we segregate the left hand side. The segregated left hand side, the figure will be something like this. Okay, I just segregate it. Okay, so this will be E1, this is C1. Okay, this point here should have a positive, what you call this, polarity, and this should be with a negative polarity. And if we try to get our voltmeter here, the voltage across this terminal is termed to as V sub L, and that V sub L is termed to as the node voltage. Okay, and this node here emanates from this title of the topic. Okay, so the purpose of this free body diagram is to compute for the value of V sub L. Okay, that will be the segregated circuit of the left hand side if we try to disengage. Okay, we cut it here. Okay, this portion here is this one. If I will cut it here, then I will try to take the free body diagram of the load. It will be figure number 2. Okay, this is the load. This point here is this point, and this point here is this. Okay, this is load CL. The current is downward, and if we try to get our voltmeter, if we tap our voltmeter over here, okay, the reading should be V sub L still, the one we are looking for. Okay, for the right hand side, we segregated it already, right? So we segregate this one, and the resulting figure will be this, right? This is C sub 2, this is E sub 2. This point here is same as this point, same as this point, okay? We just disengage them, right? And again, if we try to get our voltmeter, if we try to tap our voltmeter over here, what should come out should still be V sub L. Okay? So from the 3 given figures, we will now try to formulate the relationship of the voltages and currents, including the impedances. Okay? So considering figure E1, or figure 1. Considering figure 1, this one. I place it here, sigma notation with the capital letter B, and D should be equal to 0. The meaning of this, if you are under the study of circuitry, the summation of voltages and D should be equal to 0, considering this loop. Okay, considering figure 1. This is a voltage source, this is a voltage drop, and the voltage across this is also a voltage drop. So if I will take the summation, okay, clockwise will be positive. The sign of E1, E1 is a voltage source, so it should be positive, right? The sign is positive. That's plus E1. Okay. The voltage across E1, it's not a voltage source. It should be a voltage drop, so the sign is minus. Minus I1 C1. Because voltage is the product of current times impedance. So the voltage across C1 will be the product of the current passing through it and times its impedance. So the voltage across C1 will be the product I1 C1 and the voltage across this terminal here. Okay, it should be V sub L. It should also be a voltage drop. Okay, it's not a voltage source. So this is minus V sub L and this should be equal to 0. If we try to compute for I sub 1 will be, we put this on the right, we rearrange, therefore I1 now will be E1 minus V sub L over C1. We call that equation number 1. We are now formulating our own equation involving the currents, okay? So this is now, it seems we are on algebra, okay? Because under the study of algebra, okay, try to formulate your own equation. That's your problem, right? Or that's our problem. So after taking the summation of the voltages, considering figure 1, what comes out as an equation is I1 is equal to E1 minus V sub L over C1. We call that equation number 1. Consider figure number 2. Okay, try to take the summation of the voltages. Okay, the summation will be something like this. That's why I place it here. Clockwise should be positive. Okay. Plus I sub L, C sub L. Okay. It seems this is a voltage source considering figure number 2. But the voltage across this, it should be a voltage drop. So this is minus V sub L. There are only two, right? The voltage across this and the voltage across this. Meaning to say, the voltage across C sub L should be equal to V sub L. Or if we try to bring out the summation of voltages, okay, same as the first one. Plus I sub L, C sub L, minus V sub L, and this should be equal to 0. If we try to compute for I sub L will be, after the transposition, it will be V sub L over C sub L. That will be equation number 2. Okay? Consider figure 3. Consider figure 3. Figure 3 is this. Where's figure 3? We'll take the summation of voltages. It should be, the trace will be like that. Okay, it should be plus, right? Counterclockwise will be plus. We start with E2. From minus to plus, this is a voltage source. So this is plus E2. The voltage across C2, it's a voltage drop. Okay, it's a voltage drop. So this is minus I2 C2. And if we try to get our voltmeter, if we try to tap it here, okay, it should be a voltage drop. It's not a voltage source, it's a voltage drop. So this is minus VL, okay, and this should be equal to 0. And if we try to compute for I sub 2 we transpose to the right, then we rearrange. Therefore, I sub 2 will be E2 minus V sub L over C sub 2, and that will be equation number 3. Okay? So we have already formulated our equations involving the currents passing through Z1, passing through C2, and passing through the load CL. Okay? And to bring out the final equation and how to compute for the value of BL. Because the concentration of the problem is on how to compute for the value of BL. Because if we know BL, okay, we divide that by its impedance, that will be the total current drawn by CL. Okay? Consider node X. Where's node X in the figure? Node X is this one. That's why we call it Nodal's theorem, right? This one. This is a node. Right? Node or junction. On this junction, to get the relation of I1, IL, and I2, the current going here is actually I1, right? And the current going in here also is I2, right? And the current going out is I sub L. So if I will try to cut this portion here, it will be this. That's the junction, or node X. At node X or junction X, the current going in is I1. The current going in is also I2. The current going out is I sub L. So if we try to take the sigma notation, capital letter I, this should be equal to 0. The summation of current at junction X, I will put the subscript X here. Meaning this X here refers to this junction or node. The summation of the current at junction X should be equal to 0 with the notation. Current going in is plus and current going out is minus. Okay? Current going in is plus I1. Current going in also is plus I2. Current going out is I sub L. It should be minus I sub L, and this should be equal to 0. This is now our equation number 4. Okay? So we now have 4 equations. Okay? And actually we have determined already the relations. So what we will do? We will try to substitute equation number 1, equation number 2, equation number 3, to the derived equation number 4. Equation number 1, I1 is actually E1 minus B sub L over C1. It is this. Right? And the value I2, where is I2? It is the difference of E sub 2 minus B sub L over C2. Right? That's I2. Okay? Minus I sub L. But what is I sub L? From equation number 2, I sub L is B sub L over C sub L. So this is minus B sub L over C sub L, and this should be equal to 0. Okay? So if we try to simplify this one, okay, we can expand this one. 2 numerators by single denominator. So this should be E1 over C1. Okay, minus B sub L over C1. Okay. Also this one, we could expand this one. 2 numerators, single denominator. So we could distribute the common denominator. So this should be E2 over C2 minus BL over C2 minus BL over CL. And if we try to simplify this one, all negative terms on the right, okay? So this should be on the right, on the right, on the right. Then we'll try to factor out the common factor B sub L. So this is B sub L times the quantity. If this is on the right, then we try to transpose this to this will be the arrangement, right? So B sub L common factor times 1 over C1 plus 1 over C2 plus 1 over CL close quantity equal to what remains on the left, okay, is E1 over C1 and E2 over C2, but we place it already on the right after the rearrangement. So on the right hand side, it will be E1 over C1, E2 over C2. And if we try to compute for the value of B sub L, the node voltage, which is required in the computation of I sub L, B sub L now, okay, will be E1 over C1 plus E2 over C2 all over the summation of 1 over C1, 1 over C2 plus 1 over CL. Okay? This is the formula that was derived in the computation of the current of the value of B sub L for us to determine the current I sub L. Because for the given problem, E1 is given, right? E2 is given, Z1 is given, okay, Z2 is given, C1 is given, C2 is given, CL is given. So on the formula for B sub L, all the values on the right hand side are all given. So it is just a matter of substitution and using your knowledge of the so-called polar to rectangular and some other things, we could compute for B sub L. After the computation of B sub L, to compute for the current passing through Z sub L, I will just take that value of B sub L, we divide that by C sub L, and that the unit will be in amperes. Okay, that's it. So in general now, if there are n voltage sources of MF, so I place it here. Am I still on there now? For n sources of MF connected in perfect parallel connection, okay, supplying a common load, the computation of B sub L, if there are n sources of MF, n numbers, okay, we do not know. It could be 3, it could be 4, it could be 5. But at least there should be 2. Our given example is 2, right? So in general now, if there are n sources of MF, BL should be equal to E1 over C1 plus E2 over C2 plus dot E sub n over C sub n, that's the total numerator, all over. The denominator will be 1 over C1, 1 over C2 plus dot 1 over C sub n. It depends on how many is the number of n. The last part is plus 1 over C sub n. So that will be the formula on how to compute for the value of P sub L for n sources of EMF. So after the computation of B sub L, we divide that by C sub L, and that will be the current, okay, passing through that load. If there are n sources of EMF, and the unit is still amperes. Okay? Okay, that's it, guys. So for those of you who are taking up electrical engineering, okay, if you want to subscribe to my channel is at youtube.com/@prof.dvj.de. If you want to share it, please click share. Okay, the subject matter for tonight was very interesting because this is the real application of alternating current circuit problems. If there are n sources of EMF which are connected in parallel, supplying a common load current to a value C sub L. Okay, good evening from Los Angeles. Professor David J. De Los Reyes.